Welcome to Math 4 and the subject Differential and Integral Calculus. So we define first what is differential calculus, part of calculus that deals with the variation of a function with respect to changes in the independent variable or variables by means of the concepts of derivative and differential. Differentiation is an operation that allows us to find a function that outputs the rate of change of one variable with respect to another variable. It means we will be dealing with the rate of change. And our first lesson, limits. We say that the limit of function of x is L as x approaches a, and write this as limit x approaches to a with a function of x is equal to L. So the limit of x approaches to a with a function of x is equal to L, provided we can make function of x as close to L as we want for all x sufficiently close to a from both sides without actually letting x be a. And we have two types of limits: right-handed limit and left-handed limit. For right-handed limit, we say limit at x approaches to a positive with a function of x is equal to L, provided we can make function of x as close to L as we want for all x sufficiently close to a with x greater than a without actually letting x be a. While left-handed limit, we say limit x approaches to a negative with a function of x is equal to L, provided we can make function of x as close to L as we want for all x sufficiently close to a with x less than a without actually letting x be a. It means that x for the right-handed limit is more than the value of a, while the left-handed limit, the x is less than the value of a. Facts about limit. Given a function of x, if the limit x approaches to a positive with a function of x is equal to the limit of x approaches to a negative with a function of x is equal to L. It means that the right-handed limit and the left-handed limit has the same value, which is equivalent to L. Then the normal limit will exist. Likewise, if the limit of x approaches to a with a function of x is equal to L, then the limit of x approaches to a plus with a function of x is equal to the limit of x approaches to a minus with a function of x is equal to L. This fact can be turned around to also say that if the two one-sided limits have different values, limit of x approaches to a plus with a function of x is not equal to the limit of x approaches to a negative with a function of x, then the normal limit will not exist. Limits properties. First, we assume that the limit of x approaches to a with a function of x and the limit of x approaches to a, g as a function of x, exists that x or c is any constant. Then, number 1, the limit x approaches to a with c multiplied with the function of x is equal to, extract the constant c or c multiplied by the limit of x approaches to a with a function of x. In other words, we can factor a multiplicative constant out of a limit. So we extract c, then we find the limit of the function of x. Number 2, the limit x approaches to a with a function of x plus minus g function of x is equal to the limit of x approaches to a with a function of x plus minus the limit of x approaches to a g as a function of x, which means we separate the function of x and the g function or gx. So take the limit of a sum or difference. All we need to do is take the limit of the individual parts and then put them back together with the appropriate sign. This is also not limited to two functions. This fact will work no matter how many functions we've got separated by a plus sign or a negative sign. Property number 3. The limit of x approaches to a with a function of x multiplied by a gx is equal to the limit of x approaches to a with a function of x multiplied by the limit of x approaches to a with g with a function of x. We take the limits of products in the same way that we can take the limit of sums or differences. Just take the limit of the pieces and then put them back together. Also, as with sums or differences, this fact is not limited to just two functions. Property number 4. The limit of x approaches to a with a function of x over g of x, which means division and or quotient, and it is equivalent to separate the limit of x approaches to a with a function of x divided by the limit of x approaches to a and g of x, provided the limit of x approaches to a with g of x is not equal to 0. As noted in the statement, we only need to worry about the limit in the denominator being 0 when we do the limit of a quotient. If it were 0, we would end up with a division by 0 error, and we need to avoid that. Property number 5. The limit of x approaches to a with a function of x and exponent n. And we say the limit of x approaches to a with a function of x with exponent n, where n is any real number. In this property, n can be any real number, a positive, a negative, an integer, a fraction, irrational, 0, or etc. In the case that n is an integer, this rule can be thought of as an extended case of 3. For example, consider the case of n is equal to 2. The limit of x approaches to a with a function of x with n and exponent 2 is equal to the limit of x approaches to a with a function of x multiplied by the function of x. Using property 3, the limit of x approaches to a with a function of x multiplied by the limit of x approaches to a with a function of x, or limit of x approaches to a with a function of x exponent 2. And the same can be done for any integer n. Property number 6. The limit of x approaches to a with an nth root of a function of x is also equal to the nth root of the limit of x approaches to a with a function of x. This is just a special case of the previous example. The limit of x approaches to a with the nth root of a function of x is equal to the limit of x approaches to a, open parenthesis, function of x, close parenthesis, with an exponent of 1 over n, which means the square nth root is equivalent to 1 over n. Property number 7. The limit of x approaches to a with c is equal to c, where c is any real number. In other words, the limit of a constant is just a constant. You should be able to convince yourself of this by drawing the graph of function of x is equal to c. So any limit with a constant is always equal to constant c. Property number 8. The limit of x with x approaches to a is equal to a. As with the last one, you should be able to convince yourself of this by drawing the graph of function of x is equal to x. same thing as the limit of c, or x approaches to a, is equal to c, or a real number. Here, a function of x, or x is approaches to a, is equal to a, then function of x is equal to x. Property number 9. The limit of x approaches to a with x with an exponent n is equal to a exponent n. This is really just a special case of property 5 using function of x is equal to x. Example for limit. Limit of x approaches to 2 with a function of x squared minus 4 divided by x minus 2. And if we substitute the value of x to 2, wherein 2 squared minus 4 divided by 2 minus 2, or 4 minus 4 is 0, all over 2 minus 2 is also 0, which is undefined. Then, let's check if we can eliminate the denominator by simplifying the numerator. So x squared minus 4 is also equivalent to the square of the first and second square, or term, with a negative sign, or x minus 2 times x plus 2, and divide with the denominator, which is x minus 2. And we have similar terms for the numerator and denominator, which is x minus 2, x minus 2. Then we cancel out x minus 2, and the remaining is x plus 2. And we substitute the value of x to 2, or 2 plus 2, or equivalent to 4. So, the limit of x approaches to 2 with a function of x squared minus 4 all over x minus 2 is equivalent to 4. Next example. The limit of x that approaches to 3 with a function of x squared minus 9 all over x minus 3. If we substitute with the same value to 3, what will happen? So 3 squared minus 9 all over 3 minus 3, or 3 squared is 9 minus 9 is 0. All over 3 minus 3 is also 0, which is also undefined. Then, let's try to check if we can eliminate the denominator by using the simplification for the numerator, wherein x squared minus 9 is the same as the first and second term square and with a negative sign, or the formula is x minus 3 times x plus 3, and then we divide with x minus 3, and then we have the same terms sa numerator and denominators. We cancel out x minus 3 and x minus 3, and the remaining value is x plus 3. That's the time we can substitute the value of x to 3, or 3 plus 3, or equivalent to 6. Or the limit of x approaches to 3 with a function of x squared minus 9 all over x minus 3 is equivalent to 6. Another example. The limit of x approaches to 6 wherein a function is x squared plus 2x plus 5. And we don't have denominator. We simply substitute the value of x to 6, wherein 6 squared plus twice of 6 minus 5, or 6 times 6 is 36, plus 2 times 6 is 12 minus 5, or 36 plus 12 is 48 minus 5, or 43. So the value is equivalent to 43. Next example. The limit of x approaches to 3 with a function of x cubed minus 27 all over x minus 3. And let's check the exponent for the numerator is cube, and using the cube of the first term and second term with a negative sign, the formula is, so a cubed minus b cubed is equivalent to a minus b times a squared plus ab plus b squared. Then, what is our a. X cubed minus b cubed is 27, so therefore it is 3 cubed. And then we substitute the given value to x minus 3, and a squared is x squared minus or plus sign of ab or x3 or 3x plus b squared or 3 squared, and close parenthesis divide by x minus 3. Then we have similar terms in numerator and denominator, so we cancel out x minus 3 and x minus 3, and the remaining value is equivalent to, and the remaining value is x squared plus 3x plus 9, and we can substitute the limit x to 3, or 3 squared plus 3 times 3 plus 9, or equivalent to 9 plus 9 plus 9, or it is equivalent to 9 plus 9 is 18 plus 9, it is 27. So the value for the limit is equivalent to 27. The limit of x approaches to 3 with a fraction of 1 over x minus 1 over 3, and divide to x minus 3. Okay, so that we can eliminate the denominator of the first numerator, we need to multiply by the LCD of the first LCD in the numerator, which is x and 3, or 3x, the same, we divide by 3x, and then we simplify. 3x times 1 over x is equivalent to 3 minus, follow the sign, and 3x over 3 is equivalent to x, and then we divide, just copy x minus 3, open close parenthesis, times 3x, and then take note, we have almost the same similar terms for the numerator and denominator except for the negative sign. What will we do? We extract the negative sign, so negative 1 times 3, or negative 3, or for simplification we need to arrange. It should be the variable, which is negative positive x, then minus 3, which is also as 3 minus x, and we divide x minus 3, open close parenthesis, times 3x, and we have the same numerator and denominator, so we cancel out x minus 3, and the remaining value, it is negative 1 of 3x, and that's the time we substitute the value of x to 3, or negative 1 over 3 times 3, or it is equivalent to negative 1 over 9. So the function, or the limit, is equivalent to negative 1 over 9. Next example. What if we have a radical? So let's try radicals. So the limit of x approaches to 9 with a square root of x minus 3 divide by x minus 9. So let's try if we can eliminate the square root, especially in the numerator. Okay, what shall we do? We try to make a perfect square in the numerator so that we can eliminate the square root. So what shall we do? We need to conjugate, and it is a form conjugate, which means conjugate. conjugate. It means it's formed by changing the sign between two terms in a binomial. So we have a binomial, square root of x minus 3. And we follow the term, square root of x, and we change the sign, plus 3. And the same, we divide by the square root of x plus 3. And then, what will happen to the square of the binomials? Then, it will be the square of the first term minus the square of the second, or the square root of x squared minus the square of the second term, all over x minus 9, open close parenthesis, and square root of x plus 3. And square root of x squared is x of 3 squared, or 9. And then we divide by x minus 9 square root of x plus 3. And then we have a similar term, numerator and denominator, which is x minus 9 cancel out, and the remaining value is, for the numerator, it is equivalent to 1, and the square root of 3 of x plus 3. Then that's the time we substitute the value of x, which is 9, or 1 square root of 9 plus 3. And what is the square root of 9? It is equivalent to 3. So 3 plus 3, or it is equivalent to 1 over 6. So the limit is equivalent to 1 over 6. Another example for radicals with the limit x approaches to 4 with a function of 1 square root of x minus 1 half divided by x minus 4. Then we get the LCD for the denominator, which is 2 square root of x, so 2 square root of x, and we divide also with 2 square root of x. And then we simplify. 2 square root of x times 1 over square root of x is equivalent to 2 minus 2 square root of x over 2, which is equivalent to square root of x. And then we divide by, just copy the denominator, which is x minus 4, open close parenthesis, 2 square root of x. Then, to eliminate the square root of, or the square root in the numerator, we need to follow the conjugate, which is, we find the square of the first term and the second term with a negative sign, or we multiply by 2, except for the sign, we change for the sign with a positive sign and square root of x, and we divide the same, 2 plus square root of x. And then if we FOIL this method, 2 squared, which is equivalent to 2 minus square root of x times 2 plus square root of x, is the equivalent to the square of the first followed by a negative sign and the square of the second term, which is 2 squared minus the square root of x squared, and then divide by x minus 4, 2 square root of x times 2 plus square root of x. And then we simplify, which is 4 minus x all over x minus 4, and open close parenthesis, 2 square root of x times 2 plus square root of x. And then 4 minus x all over x minus 4 is almost the same, except we extract negative sign, so negative 1, and always first term should be in variable form and the second term should be in constant, or x minus 4 divided by x minus 4, then 2 square root of x, open close parenthesis, times 2 plus square root of x, and we cancel out x minus 4 for the numerator, and the denominator is also x minus 4. And the remaining value is negative 1, and 2 square root of x times 2 plus square root of x. And we simplify or substitute the value where x is approaches to 0. So negative 1 of 2 square root of 4 times 2 plus square root of 4, or equivalent to negative 1 of 2 times 2, then 2 plus 2, or equivalent to negative 1 of 4 times 4, which is equivalent to negative 1 over 16. So the limit is equivalent to negative 1 over 16. For the next example, what if the x approaches to infinity? For example, limit of x approaches to infinity, and the function is 1 over x. Okay, if we change, if x is equals to 100, what will happen to the function, which is 1 over 100, or equivalent to 0.01? What if x is equals to 1000, which is 1 over 1000, and the value is 0.001? It means if the value is increasing to infinity, the function 1 over x approaches to 0. Then another example, if the limit of x approaches to infinity with 8x plus 2 all over 2x minus 5. If the limit is approaches to infinity, the constant, even in the numerator or denominator, is negligible. So that's why if you see a constant in the numerator and denominator, if the x is approaches to infinity, the value for the constant in the numerator and denominator are negligible. Okay, try. If f or x is equal to 1000, what will happen to the function? So 8 times 1000 plus 2 divided by 2 times 1000 minus 5, or this is equivalent to 8000 plus 2 divided by 2000 minus 5, or this is 8002 divided by 2, or 2000 minus 5 is 1995, or equate to whole number. It is also 8000 divided by 2000, which is equivalent to 8000 over 2000 is equivalent to 4, which means if the limit x approaches to infinity, the value for this function is equivalent to 4. Then we can say that the constants are negligible. Okay, let's try if we compute based on the fraction. Okay, let's try. If we eliminate the value of x, take note, in our first example, the limit of x approaches to infinity with a function of 1 over x, the value is always 0. What if we change the constant to a fraction? Therefore, the highest exponent is 1. So therefore, we need to multiply by a fraction of 1 over x. Same thing with the denominator, which is 1 over x. Then simplify. 8x times 1 over x is equivalent to 8 plus 2 times 1 over x, it is equivalent to 2 over x. And then we divide by 2x over times 1 over x, or equivalent to 2, follow the sign, minus 5 times 1 over x, or 5 over x. Then, based on the limit, so 8 plus the limit of x approaches to infinity with, okay, we take out the 2, so 2, limit of x approaches to infinity with 1 over x, divide by 2, the constant, minus, extract the 5, and then we put the limit of x approaches to infinity with 1 over x. In our first example, the limit of x approaches to infinity with a function of 1 over x is always equal to 0. So therefore, 2 or 8 minus twice of the limit of x approaches to infinity of function 1 over x is equal to 0. All over 2 minus the constant 5 and multiply by the limit of x approaches to infinity with function of 1 over x, also to 0, and the value is 8 over 2, which is equivalent to 4. So therefore, the limit of x approaches to infinity with a function of x plus 2 all over 2x minus 5 is equal to 4. Another example. The limit where x approaches to infinity and the function is 9x squared minus 3x divided by 5x minus 3x squared plus 2, and that's the function. Then it's infinity. Previously we have the limit of x approaches to infinity with a function of 1 over x is always equal to 0. So let's try. And the highest constant or exponent in the variable is square. So therefore, we need to multiply it by a fraction of 1 over x squared for the numerator and divide also by 1 over x squared. And then simplify. So 9x squared times 1 over x squared is equivalent to 9 minus 3x times 1 over x squared is equivalent to 3 over x. And then we divide. 5x times 1 over x squared, it is equivalent to 5 over x. Follow the sign, minus 3x squared times 1 over x squared, it is equivalent to negative 3. And plus 2 times 1 over x squared, it is 2 over x squared. And then change it to the limit. So 9, the constant, minus, extract the 3, then we put the limit of x approaches to infinity with a value or a function of 1 over x. And then we divide. Extract 5 and the limit of x approaches to infinity with 1 over x minus 3, the constant, plus extract the 2 and the limit of x approaches to infinity with 1 over x squared. And then if the limit x approaches to infinity with a function of 1 over x always approaches or equal to 0, therefore 9 minus 3, which is the limit of x approaches to infinity with 1 over x, always equal to 0, all over 5 times the limit of x approaches to infinity with function of 1 over x is also 0, minus 3 plus twice of the limit of x approaches to infinity with 1 over x squared, whether x cubed, x to the fourth, the value is always 0. So 2 times 0, and 9 over negative 3. 9 over negative 3 is equivalent to negative 3.